Introduction to atomic structure and its technological applications. Atoms are the fundamental building blocks of matter, and understanding their structure is key to unlocking the mysteries of the physical world around us. The structure of an atom, composed of a dense nucleus containing protons and neutrons, surrounded by orbiting electrons, not only defines the properties of elements, but also explains how atoms interact, bond, and form the materials we encounter every day. At the atomic level, electrons, protons, and neutrons dictate how substances behave, react chemically, and interact with energy. This atomic structure is not merely a concept confined to the world of chemistry. It has profound implications for a wide range of modern technologies. From the development of semiconductors in electronics to advances in medical imaging and treatment, to the revolutionary potential of nanotechnology and energy storage, the manipulation of atomic properties drives much of today's technological progress. This deep understanding of atomic interactions also forms the foundation for cutting-edge fields such as quantum computing, nuclear energy, and material science. As technology continues to advance, so too does our ability to control, manipulate, and harness the power of atoms, opening up new possibilities for innovation in industries ranging from medicine to renewable energy. The study of atomic structure is not just fundamental science, but also the driving force behind the technological revolution reshaping our world. An atom is the basic building block of matter, the smallest unit of an element that retains its chemical properties. Everything around us, from solids and liquids to gases, is made up of atoms. Let's break it down. 1. What is an atom? An atom consists of three main components. Protons. These are positively charged particles found in the nucleus, center, of the atom. Neutrons. These have no charge, neutral, and are also located in the nucleus. Electrons. These are negatively charged particles that orbit around the nucleus in different energy levels or shells. 2. What does an atom contain? Nucleus. The dense, central part of the atom, consisting of protons and neutrons. Electron cloud. The region surrounding the nucleus where electrons are likely to be found. Electrons orbit the nucleus in shells or energy levels. 3. Proof that every matter has atoms. The concept that matter is made of atoms has been supported by many lines of evidence and scientific theories over time. Here are some key pieces of proof. A. Atomic theory. John Dalton, 1803. John Dalton proposed that matter is made up of indivisible atoms in 1803, based on experiments in chemistry. His theory laid out the idea that atoms of different elements have different masses and combine in fixed ratios to form compounds. B. Brownian motion. Robert Brown, 1827. Robert Brown observed that tiny particles suspended in a fluid moved randomly, called Brownian motion. This motion was later explained by scientists as the result of atoms and molecules in the fluid colliding with the particles. This behavior could only be explained if matter were made up of tiny, invisible atoms. C. The electron. J.J. Thomson, 1897. J.J. Thomson's discovery of the electron provided direct evidence of atomic structure. His experiment showed that atoms could be divided into subatomic particles, and the existence of the electron revealed that atoms were not indivisible as previously thought. D. X-ray crystallography, 20th century. This method, which involves directing X-rays at a crystal and analyzing the pattern of diffraction, helped to reveal the arrangement of atoms in solid materials. It directly confirmed that matter has a highly ordered atomic structure, visible in the diffraction pattern. E. Scanning tunneling microscopy, STM, 1981. The most direct evidence for atoms came with the invention of the scanning tunneling microscope. This tool allows scientists to see individual atoms on a surface by scanning the surface with a sharp tip. The images produced by STM allow us to directly observe the positions of atoms and even manipulate them, providing undeniable proof that atoms are the fundamental units of matter. F. Chemical reactions. When matter undergoes a chemical reaction, atoms are rearranged but not created or destroyed. This is known as the law of conservation of mass, which implies that atoms are the basic units involved in chemical transformations. The observation that matter behaves in predictable, quantifiable ways during chemical reactions supports the atomic theory. G. Nuclear reactions. Nuclear reactions, such as those in the sun or nuclear power plants, provide further proof of the existence of atoms. The energy released in these reactions comes from changes in atomic nuclei, showing that the nucleus itself, which is made of protons and neutrons, is central to how atoms behave. An atom is made up of protons, neutrons, and electrons. Every form of matter, whether solid, liquid, or gas, is made up of atoms. The evidence for atoms comes from multiple scientific discoveries, including Brownian motion, the discovery of the electron, and advances in microscopy, all of which support the idea that matter is composed of tiny, indivisible particles called atoms. Deep dive into atomic structure. At its core, the atomic structure is the arrangement of subatomic particles within an atom. Understanding this structure is crucial because it explains how atoms interact with each other, form bonds, and give rise to the properties of materials. Let's explore the atomic structure in more depth. 1. Components of an atom. A. The nucleus. Protons. These are positively charged particles found in the nucleus. The number of protons in an atom determines the element's identity. E.g., hydrogen has 1 proton, helium has 2. Neutrons. Neutrons have no charge but contribute to the mass of the atom. They stabilize the nucleus. The number of neutrons, along with protons, determines the isotope of the element. E.g., carbon-12 and carbon-14 are isotopes of carbon. The nucleus, which contains protons and neutrons, is very small relative to the entire atom, but contains nearly all of the atom's mass. B. Electrons. Electrons are negatively charged particles that orbit the nucleus in electron shells or energy levels. Electrons are much smaller than protons or neutrons. They are responsible for chemical bonding and interactions. The distribution of electrons in shells follows the Bohr model and the quantum mechanical model. For example, the first shell can hold 2 electrons, the second can hold 8, and so on. The outermost electrons, in the valence shell, are especially important in determining how atoms interact with each other to form molecules. 2. Energy levels and orbitals. Electrons are arranged in orbitals, which are regions of space where there is a high probability of finding an electron. The quantum mechanical model explains that electrons don't follow fixed orbits, as suggested by Bohr, but rather exist in cloud-like regions around the nucleus. These orbitals are organized into energy levels or shells and sublevels, e.g. s, p, d, f, which describe different shapes and orientations of electron clouds. 3. Atomic number and mass number. The atomic number, denoted by Z, is the number of protons in an atom's nucleus, which also determines the element. For instance, hydrogen has an atomic number of 1 because it has 1 proton. The mass number, denoted by A, is the sum of protons and neutrons in the nucleus. For example, carbon-12 has 6 protons and 6 neutrons, so its mass number is 12. How atomic structure is used in technology. Understanding the atomic structure is crucial for the development of various technologies, ranging from electronics to medical applications. Here are some key areas where atomic structure plays a significant role. 1. Electronics and semiconductors. The properties of electrons and atoms are fundamental to the functioning of electronic devices, such as computers, smartphones, and LED lights. Semiconductors. Materials like silicon are made up of atoms that have 4 electrons in their outer shell. This gives them special electrical properties. By manipulating the atomic structure of semiconductors, scientists can create materials that conduct electricity in some conditions but not in others. This is done by doping the semiconductor with other elements, e.g., phosphorus or boron, which adds free electrons or creates holes that carry charge. Transistors, the building blocks of modern electronics, rely on this concept. A transistor can act as a switch controlling the flow of electrical current. By controlling the arrangement of electrons, transistors amplify signals and make computation possible. Quantum dots. These are tiny semiconductor particles, whose electronic properties are determined by their size and shape at the atomic scale. Quantum dots are used in advanced displays, solar cells, and medical imaging because their behavior changes when manipulated at the atomic level. 2. Nuclear technology. The atomic nucleus is at the heart of nuclear energy and nuclear weapons. Understanding the behavior of protons and neutrons in the nucleus is essential for nuclear fission. This is the process where heavy atomic nuclei like uranium-235 split into smaller nuclei, releasing a massive amount of energy. This process powers nuclear reactors and is also used in atomic bombs. Nuclear fusion. Fusion occurs when two light nuclei like hydrogen combine to form a heavier nucleus, releasing energy. This is the process that powers the sun. Scientists are working on harnessing this process for clean energy. 3. Medical technology. Atomic structure is crucial in developing diagnostic and therapeutic technologies. X-rays and CT scans. These medical imaging techniques rely on the interaction of high-energy photons with atoms in the body. Different tissues absorb X-rays to different extents, allowing for detailed images of the inside of the body. Radioisotopes. Certain isotopes, atoms with an unstable nucleus, are used in medical treatments and diagnostic imaging. For example, radioactive iodine is used to treat thyroid cancer, and positron emission tomography (PET) scans use isotopes that emit positrons to create images of internal processes in the body. 4. Nanotechnology. In nanotechnology, manipulating matter on the atomic or molecular scale is essential for designing new materials with unique properties. Nanomaterials. By controlling the atomic arrangement in materials like carbon, e.g. graphene, scientists can create super strong, flexible, or conductive materials. These materials have a wide range of applications in everything from electronics to medicine. Nanoparticles. These are materials with sizes on the order of a few nanometers, 1 nanometer, 10 nanometers. Their properties are often distinct from bulk materials due to the arrangement of atoms at such small scales. For example, gold nanoparticles are used in targeted drug delivery because their small size allows them to pass through biological membranes. 5. Energy storage and batteries. Atomic structure plays a role in the functioning of batteries and energy storage devices. Lithium-ion batteries. The movement of lithium ions between the anode and cathode involves the transfer of electrons at the atomic level. By manipulating the atomic structure of materials used in batteries, we can increase energy density and extend battery life. Fuel cells. These devices use chemical reactions at the atomic level to convert chemical energy into electrical energy. For example, in hydrogen fuel cells, hydrogen atoms combine with oxygen atoms to form water and release electricity. 6. Material science. Atomic structure directly influences the properties of materials, from their strength to their conductivity. Alloys. By arranging different atoms in a specific pattern, e.g., combining iron with carbon to make steel, we can produce materials with specific desired properties like increased strength or resistance to corrosion. Superconductors. Certain materials, when cooled to extremely low temperatures, can conduct electricity without resistance. This phenomenon depends on the way atoms and electrons interact at very low temperatures. 7. Atomic clocks and GPS. Atomic clocks, which use the vibrations of atoms, often cesium or rubidium, to keep time, are crucial for technologies like GPS. These clocks rely on the fact that atoms emit electromagnetic radiation at precise frequencies when their electrons jump between energy levels. By measuring the frequency of these emissions, we can keep very accurate time, which is essential for determining precise locations on Earth. Atomic structure describes the arrangement of protons, neutrons, and electrons within an atom, which governs the atom's chemical and physical properties. This structure is the basis for many technological advancements, including electronics, semiconductors, transistors, nuclear energy, fission, fusion, medical applications, imaging, therapy, and nanotechnology, materials, nanoparticles. Understanding atomic interactions enables scientists to design materials, devices, and systems that power modern technology, from smartphones to medical diagnostics and energy storage solutions. Summary of atomic structure and its technological applications. Atoms, the basic units of matter, form the foundation of everything around us, from the air we breathe to the devices we use. An atom consists of a nucleus, made up of protons, positively charged particles, and neutrons, neutral particles, surrounded by electrons, negatively charged particles, that orbit the nucleus in specific energy levels or shells. The number of protons determines the elements, while the arrangement of electrons governs an atom's chemical behavior and its ability to form bonds with other atoms. Understanding the atomic structure is pivotal because it explains not only the physical properties of matter, but also its chemical properties. For example, the way atoms bond together to form molecules, the way electrons move within atoms, and how energy is exchanged during chemical reactions are all outcomes of atomic interactions. This atomic structure is also the reason why substances behave differently. The arrangement of electrons in different shells dictates how atoms interact with each other, how they absorb or emit energy, and how they bond to form larger structures. The study of atomic structure extends beyond theoretical understanding into a realm that impacts our daily lives. From the tiniest components of electronic devices to the vast networks of nuclear power plants, atomic behavior is at the heart of modern technology. Here are several key technological fields where atomic structure plays a crucial role. 1. Electronics and semiconductors. At the core of modern electronics lies the manipulation of atoms, especially the electrons that orbit the nucleus. Semiconductors, such as silicon, are engineered by controlling the number and behavior of electrons in their outermost shell. By doping semiconductors with other elements, scientists create materials that can conduct electricity under certain conditions, leading to the development of transistors. These tiny components, which act as switches, form the backbone of all digital devices like smartphones, computers, and televisions. By controlling the flow of electrons, we can process information and amplify signals, enabling modern computing. 2. Nuclear technology. Nuclear energy relies on the manipulation of atomic nuclei, the dense center of atoms. Nuclear fission, splitting heavy atomic nuclei like uranium-235, releases massive amounts of energy, which is harnessed in nuclear power plants. Conversely, nuclear fusion, where light atoms like hydrogen combine to form heavier elements, powers the sun and has the potential to provide clean, virtually limitless energy. Understanding atomic structure and the forces within the nucleus is fundamental to both harnessing nuclear energy for power generation and developing nuclear technologies for medicine and national defense. 3. Medical applications. Atomic theory has led to innovations in medical imaging and treatment. X-rays and CT scans rely on high-energy photons interacting with atoms in the body, producing images that allow doctors to diagnose injuries and diseases. Additionally, radioisotopes, which are atoms with unstable nuclei, are used in both diagnostic and therapeutic applications. For example, radioactive iodine targets thyroid cancer, while positron emission tomography (PET) scans use radioactive isotopes to visualize cellular activity, aiding in the detection of cancers and other diseases. The precise understanding of atomic behavior is essential for these life-saving technologies. 4. Nanotechnology. The manipulation of matter on the atomic and molecular scale, known as nanotechnology, has transformed multiple industries. Nanomaterials such as graphene, a single layer of carbon atoms arranged in a honeycomb lattice, have remarkable properties, like incredible strength and electrical conductivity. Atoms are engineered into nanoparticles that can be used in everything from medical drug delivery systems to improved materials for electronics and solar panels. The ability to design and control materials at the atomic level is revolutionizing fields ranging from pharmaceuticals to environmental sustainability. 5. Energy storage and batteries. The atomic structure of materials is also crucial for the development of batteries and other energy storage devices. For example, lithium-ion batteries, widely used in everything from smartphones to electric vehicles, rely on the flow of lithium ions between electrodes. This process involves the movement of atoms and electrons at the microscopic level. Understanding atomic interactions allows engineers to design more efficient and powerful batteries by optimizing how atoms and ions move and store energy. 6. Material science. The manipulation of atomic structures allows us to create materials with customized properties for specific applications. Alloys, such as steel, a mixture of iron and carbon, have enhanced strength and durability because of the way atoms bond together. Advances in superconductivity materials that, at low temperatures, conduct electricity with no resistancier, made possible through an in-depth understanding of how electrons behave at the atomic level. By controlling atomic interactions, scientists can design materials that are stronger, lighter, and more efficient, leading to innovations in construction, transportation, and electronics. 7. Atomic clocks and GPS. One of the most precise applications of atomic structure is in the development of atomic clocks. These clocks measure time based on the vibrations of atoms, typically cesium or rubidium, which emit electromagnetic radiation at incredibly consistent frequencies when electrons shift between energy levels. The accuracy of atomic clocks is essential for global positioning systems, GPS, which rely on precise time measurements to calculate the position of objects on Earth. The accuracy of GPS systems is only possible due to our understanding of atomic interactions and timekeeping at the atomic scale. Conclusion: at its most basic level, understanding the atomic structure of matter allows scientists and engineers to manipulate the fundamental components of nature. From the electronics in our devices to the medicine that saves lives and the clean energy solutions of the future, the principles of atomic structure are at the heart of numerous technological advancements. The atomic scale, once a theoretical realm, is now a domain where precision and innovation thrive, pushing the boundaries of what is possible in science and technology. As research progresses and technology evolves, our deeper understanding of atomic interactions promises even more breakthroughs that will shape the future of everything from communications to energy, healthcare, and beyond.